Okay. A very good evening to all of you who are listening to this a session of a ShoAIcase Series. This is a place for the startups to come and demonstrate their products. I'm Gayatri Devi. I'm the India chapter president of Applied AI Association. The association is formed in the US sometime last year in July, August, and India chapter has been functional since January. We've started putting up all events together in the process of educating the AI illiterates or people who are wanting to learn more on AI. That's the whole mission of the association itself. I hope you enjoyed this session. This is especially for startups. We have this almost every alternate Thursday. Look out for these sessions coming up. This is the fourth episode, but just the third startup that we are hosting. I would welcome Antony Alappatt as part of this session. He's going to be walking us through what Axon and Karmic Intelligence stand for. He will be taking us through the next hour or so. The session is divided into two parts. He's going to be talking for the first 20-30 minutes about the product, and we allow him to demonstrate and showcase his product. The second part of the session is for Q&A. So we will, depending on how many questions we have, how many people join in as we go by, we will kind of plan the session. With that, I turn it around to Antony. Thank you so much for doing this, Antony. Over to you. Please take over from here.
Thank you, Gayatri, for giving me this opportunity to talk in this forum. Am I audible?
Yes, you are.
Okay. So my name is Antony. I've been in the industry since 1985. I've been in all aspects of technology from 4004 microprocessor to here. So I've been all aspects of the technology, and this is the motivation for doing this is as part of as an MIS director, I had issues trying to solve problems for the enterprise, and this is my answer to that. I felt that there's something wrong fundamentally in terms of computer science. So this is answer to that problem. We believe that we have fundamentally a new paradigm in next generation software. So with that, I will go to the first. So what is this new, karmic intelligence? Presently, if you look at any AI, it is a neural network that is connected together, and then the nodes are turned on or off with some weights, and the weights is programmed. And so there are many layers. You give an input, it goes through the processing layers and then produces an output, the inference output. And you can do anything with it. That's worked out for very many use cases. The problem where some happens is there are some areas where it cannot handle, like drift, where your model itself doesn't respond to, model doesn't move. So these are areas where we believe the problem is your model has to be tightened to the, just like the human being, the model has to be tightened to the environment, and it has to listen to the environment and then respond to the environment. And that is what karmic intelligence is. Basically, what we are saying is you have to move away from algorithms to more of a cause-effect process. So we view the system as a process rather than as an algorithm. So human being is a bunch of cells that interact with each other. It's the same way here. Everything is a bunch of autonomous nodes that talk to each other, and we just say what the talking interactions are. So at the end of the day, deep inside, it's just a living network. It's not a static network that we have now. If you look at currently, it's just a static network that is built at the time of training, and then it stops. Then you have to remodel. You have to retrain again. What we are saying is, if you build everything on a causation, then your model keeps changing, just like a human being, or the nature. It keeps evolving as and when the environment changes. So what we believe, so the learning is basically a change of the network. It takes a shape. The shape of the network evolves. Like in a human being, it starts with two cells. It connects, two cells merge, then it starts spawning many cells and becomes a human being. Same way. Here, we believe we model the systems like that. And so what is the advantage? You don't need data to train. You just need to model it properly. You know the causation, which every enterprise knows, the causation. So you can build the causation directly. You don't need to have correlation. You can directly build the causation. Since there are multiple agents talking to each other and they talk in transient interactions, your data is safe because it's autonomous. So, and so that's one advantage. Ultimately, when you build systems like this, it becomes more secure at the core. The break even, then what happens? Some of the challenges we have is because of the high requirement people that is required to make projects because of the fundamental sequential limitation of software. We have overcome that by moving everything as processes. So you can directly model enterprises here. So for example, the supply chain stuff we're going to show today is done in 2000 lines of code. It's just done by Jagdish and nobody else. So we can actually show metrics to say that we can actually show value. Okay. And then we don't have foundation models. Foundation models, there's no LLM models, nothing. You are given the opportunity, you're given a blank slate, and you can build the model yourself. So the model that you build in the language that we have is your own IP. So far, so basically, what does it contain? It contains two components. We call the yantra, which is the engine. That is a KI processor, the Karmic. And unlike current processor, which moves in a sequential step-by-step instruction, started by a program counter, here it is all about how agents talk to each other, which agents interact with each other. So there is no sequentiality. Everything is concurrency, and the network, the application is the living network of all the nodes. When we go to the demo, it will be very clear to you. And so now we need to model these interactions and the agents, how they talk to each other. And that is the mantra, the language in which you do that. So what does it buy you? So what we are saying is you don't need to buy a foundation model and then try to create something out of it. Here is a blank slate. You can build processes right out of that. The cause effect model is basically a process. And it's completely explainable because you know what interactions made it happen. And we can actually tell you we can show you in the demo which interaction actually happened at what time. And so you're able to know how the network progresses, network state progresses. So you don't need it's explainable. You know current state of the network. The plasticity, because it is a bunch of nodes that can talk to each other, change its shape by channels that talk to each other, it has got the same flexibility of a human brain. We can walk you through. It's a big claim, but we can show you how it is done. And obviously, because there's no training involved, it consumes less power. IP is owned by you, and there is no vendor dependence because the language is yours. Only the processor we own. We don't own the language. The IP that you create is yours. So what we are promising is, if you have a fresher like Jagdish, in 2 months, we can actually train the person in this language, and you can have an AI enterprise running, an IT department. Okay. And we have done that in real life, and Jagdish is an example. So, and then, like I said, there is security because two agents talk to each other in transient interactions. They're as single-use tokens. They talk to each other in single-use tokens. So it's secure, and everything is exposed as a hypermedia. So you can simply put this in behind the firewall and use your standard LDAP that you have, and through the firewall you can control security just like. So you are using the current LDAP and your firewall security standards. You don't need to invent anything. And ROI break even because of the reduction in code. The supply chain that we said is done in 2000 lines. And because there's no sequentiality, there's no defects. I mean, very little defects. And because it is behind a firewall and talks only on HTTP to the outside world, you have a lot of OWASP token vulnerabilities. So from here on, what I can do is I would like to take to the demo. So Jagdish, if you can show your screen, I will, if anybody has any questions, or we will.
We can park a few minutes if people have questions.
Yeah, if you have questions, we can 2 minutes, 2-3 minutes.
Yeah, I think
Otherwise
there's
we
a
can go to the
question
demo.
from Saurabh. He says, can you please shed more light on what does the environment mean? If there is no model involved, what does agent refer here? Yeah, I think you can respond to that, Antony.
When you say environment,
You can see in the chat window.
yeah, 1 minute.
There's one more from Zoom user. So
So
let's
the
go
agent,
one by one.
yeah.
So Anthony, I think the next 15 minutes you spend on answering these questions. We'll go to the demo after that. Yeah.
Correct. Okay. So a model, so traditional models are you train the model and you do it. Here, the model is the interaction, the agents that talk to each other. So agent is not agents, but autonomous agents that talk to each. I think the demo will actually clear that up for you. So if you can wait till the demo, and if it's not answerable, then we can take that up if that is okay.
That should be okay. Let's go to the next question. If there are many agents, does it need a high power hardware?
No. We don't actually. It's not multi-threaded. Each of these agents, when it's agents, not individual threads. Agents are just a concept because our language is based on something called interactions. How does agents talk to each other? It is the interface between two agents. So it doesn't use Instack. In fact, we have run this in Raspberry Pi. So it is.
So I think, Antony, as you're telling this, right, I'm just telling this to myself.
Yeah.
Forget for the next 20 minutes, forget what LLM means, what agent means, what inference means, and then listen. Because if you listen with that, I don't think we will get what you're telling.
Correct. Okay. Yeah.
Yeah, that makes sense.
Yeah. So an agent, you have to go back. There is a lot of clutter when you say agents, right? Agents, we can say it's an autonomous object. In this reference, it is an autonomous object, which is like a cell in a body. Agents, the way it is done now, it's like a batch job. You take an LLM input and then you do something and produce an LLM output, right? Here it's not like that. Here an agent. Hello?
Yeah. That was someone on muted the person. Go ahead.
Okay. So it is a slightly different. Agent here is like a cell in a body, and cells in a body only interact with each other. You just model only the interactions that happen. Okay, how does this cell signal the other cell? It's the same way here. I think again we will go through the demo. I think that will be the best. A lot of things will clear up.
Okay, if there are no other questions, let's move to the demo.
Correct. Okay. So the demo, what we are doing, So the demo, what we are planning is a supply chain, which we have done. These are some of the demo we did for a tire manufacturer. Jagdish, are you going to say this? So it is a supply chain that models So imagine a supply chain manager who um, who is struggling with all the constraints in the system. You don't know when you solve one. There are many. Imagine there is a lot of distributors, lot of dealers, and lot of there is plants. Okay, and now each of these are constraints in the system. And so so Kanyakumari dealer runs out of stock. He orders from the distributor. Then the constraint shifts from the distributor to the Kadalur distributor. And then Kadalur distributor now becomes a bottleneck. So it moves to a Chennai plant. So the bottleneck shifts dynamically. So the purpose here is to find out where the bottlenecks are. So in one screen where you can say, okay, the bottleneck is here. Okay, let's fix that. When you fix that, suddenly the bottleneck will shift somewhere else. So that is the purpose of this. So so all this, so in this case, what we are saying is, it is a tire manufacturer. So there is a R13 is a rim 13 size, and it fits WagonR and Maruti Suzuki. Okay. And so there is a reason why we are doing that navigation, because this is more to show the technology behind. You don't look at it from the perspective of a supply chain, but look at it to demonstrate what is happening at the back. So this navigation, the UI is here quite dumb. It is walking through a network at the back. Okay, so here Maruti Suzuki, he takes WagonR, it shows you a product, and it shows you the route. So in this case, it is being built in Chennai plant. It gets shipped to Kadalur. There's a distributor there, and then it goes to Bangalore and then dealers. And that is how, and depends on the lead time, the stocks have to change. Okay. So that is the whole thing. And then also the prediction. Can you show the prediction? So here, what we are saying is, so in real time, it will tell you where the bottlenecks are. The reds mean it's understock. Green means it's overstock, and there are balanced networks. Okay. So, and these happens independently. These all happen in real time, and they are all independent agents running different computations in real time. Okay. So now what we will do is we will, to show it in an example, we will connect the Kochi, like there is a Kochi dealer. What we are going to do is, so we have to show this also, right? Now what the plan we're going to do, okay, so there are two pieces. What you saw was the application. Now what you're seeing here is the backend. Okay, so here we have three pieces. There is, like I said, there's a yantra. This is the thing that creates a network at the back. Okay, so now let's start creating. Can you go back to the supply chain? Okay, we're going to connect. Can you build the network? Can you show that network? Yeah, so now what we are trying to do is we're going to show you how we will connect a Kochi dealer with a Kadalur distributor. And so now it becomes, we are adding one more spoke to the network. And okay, so now can we, so this is our console. Yantra has a console. So in this console, it is connected to an IP. This can be deployed in anywhere. And then each of these are different nodes, like distributors, plants, and there are many instances of these agents underneath that. And each of these agents have interactions. Like, for example, this one, you can create a inventory, good inventory, these are the interactions that you set up. Okay. So now we're going to do one interaction, and we're going to create a, we're connecting it to a distributor, and there's a rhythm. We'll talk about that. So what happens is, so now if we go, this is how we check whether the model is connected at the back. Okay. So now each a node has to have a, if it's an intermediate node, he will have a velocity decision, meaning he has to balance downstream and upstream. If he is an N node, then he has a basically a constraint. So he will always try to manage two. So to connect, you have to turn on what sort of constraint are you putting into this agent. So in this case, it's an edge node. So he's turning on a constraint decision. And these are interactions we set up in our language. Okay, so now what we have done is we have added one more network connection. Okay, so what has happened? So how we test the network graph is, we as a programmers, the network designers, we go through the network graph. This is how we know how the network is connected. So the same thing what you saw on the map is reflected at the back. So in the case of that blue node, can we show the blue node? Yeah. So that is actually a navigation map, right? What you saw, how we navigated, only what the UI is doing is only walking through this network map. There's no database, SQL calls, nothing. So when you go through, can you show that supply chain? Yeah, when you go through that map, Maruti Suzuki and WagonR, all the UI is doing is going through that map, network map at the back. Yeah, so in this case, Maruti Suzuki, WagonR, and it comes to this product, and that product is connected to many inventory nodes. These are the different, and they take care of all the inventory decisions, whether it's edge decision or is it what are the constraint decisions, all done by each of these independent nodes. Okay, so this network is not fixed. It keeps evolving as and when you interact with each of these nodes. In fact, nodes can be even made to cut itself off and then connect back. Just like how a human body heals itself, we can do that here. We can remove the connections and connect back around it. So this is useful in the case of a supply chain where there is a flood in one area, and then every thing has to bypass that. Then we would go this. So there is a question: what are the basis of prediction? Prediction is just we are going through only the constraint. The constraint at each. Yeah. So what we are saying is, at each node, we would see what the upstream nodes are and what the downstream nodes are, and then it comes up with whether it's overstock or understock. So that modeling will show you now. Okay, so that question, let's lead to modeling. And so the modeling can be done. What we would like to do is we would like to connect. So there are two nodes that are not connected, SUV and Mahindra, right? Now we are going to connect that to the, by interacting with those nodes, you would make the connection between those two and connect that to the tire. Okay, so can we do that? And we will show you the code that makes it happen. Yeah. So now go back to the network map, and you would see when you refresh it, you would see, where is that? Yeah, those two nodes are connected. Okay, by having one connected to the other. Now we will connect it to a product. So, and so we will connect it to RG Live. Okay, so here we will go through. So remember the select category. Okay, that is the interaction that we have to look at. And so now SUV is connected to Mahindra and it's connected to this. Now we will show you the code that makes that magic happen. It's just, so there is some XML code that, so it is a select category, and there is some interactions that tell and ask are interactions that you have to set up. Okay. That is how two endpoints bind. We can go into the, how it is done and all later, but wait. So what I wanted to show you was the next interaction is gen shared product name. Okay. Now, if you go to the history, we will be able to see how the interaction happened. So we go to the product and you go and say, okay, what are the interactions that we said when you define the interactions, they are all here. So in a way, so at any point in time, by knowing a network shape, you can actually know how the network came to this shape. So it's fully explainable why a network took its shape. Okay, and the question of prediction, are we using AI? Yeah, this is autonomous AI. This is the next where we only talk about what the agents are and how they talk to each other. I'm reading from the question that is there. Now, if you look at each of these, there is red, and those, what the UI is doing is it is reading understock, overstock actions on the left, on the right here. Okay. And so understock is shown as a red color. Overstock is shown as a green color, however you want. Okay. Now we will show you the code that actually drives that, just to show that decisions can be made in an agent. So in this case, what we are doing is we are comparing inventory quantity with the stock required, and then we have a overstock or understock signal in number 35. That's so what we are trying to say is the network is not fixed. It is evolvable. It is left to you to evolve it. It is left to you to control how the evolving happens. It is fully explainable, and and it's fully secure because the interactions are. With that, we can go to a Q&A, so we can address specific points.
Yeah, I think people can ask questions, unmute yourselves and ask questions rather than typing. That conversation might be far more engaging.
Yeah, we can make it more discussion. That will be better than, you know.
Hey, Anthony, thank you so much for, walking us through from there. So I see this is a classic case of the autonomous AI, which you have been using it, right? And I mean, correct my understanding that's in autonomous AI, we in general use a different kind of the model, either the perception language-based model, right? So, I mean, can you talk a little bit more about it? Which particular models have you used? It's a perception or the language-based model, or anything what you have used differently?
So this has come with a unique thing. We are not using any of the current models because current models are all neural network based. We are moving away from a neural network based to more of interaction based model. How does one agent talk to each other? So that is what we are doing here. So in this case,
go on, please. I'm sorry.
So what we have is underlying a new paradigm. We have a language in which we only define what the interactions are. Okay, so you can, let's take two cells. How does two cells talk to each other? Which is the, so if you want to model cells, it is rating a signal A. Okay, what happens when you test the signal A? What is the response? So basically, you are modeling the causation of, okay, if you touch this, this happens. If you touch, so that gives you present more interactions. And then that gives you more interactions, and there is a lot of interactions that keep happening.
Makes sense, Anthony, but if I was looking for the more details onto that. I understand there's like you have used these things, right? But even for the cell to remember and do any kind of the predictable analysis, have you built any of your models or any infrastructure you have used already existing models?
No, we don't. We are not using any existing infrastructure. We are using straight. It is no. We are not using any currently model infrastructure. This is entirely out of the blue. We are only modeling what the agents are and how they interact.
Oh, okay.
So I can walk you through. I mean, we can. I can take the language through, so we can go into a detailed discussion. I think that will be more clear. I mean,
yeah, sure. Thank you so much, Anthony.
Yeah, so we can actually have a a different conversation. If you can connect me, I will walk you through.
So this is very interesting, Anthony. Sorry, I'm not be able to be on cam because I'm in odd place.
No.
Now, I'm kind of relating this to whatever you kind of showed. At least with my limited thing, whatever I've seen, it seems to have a lot of basis on K-graph, and you use Neo4j for storing it and retrieving it, and there's a language for representing it. Okay. And you query a K-graph, you can get through all the interaction, and the K-graph keeps building as you add for that. Is there something it's a similar and it's an implementation of that, or is it different from a K-graph?
Yeah. So let's take Neo4j, right?
Yeah.
Neo4j is actually it's a graph database.
Correct.
It is based on a node and its edges.
Correct.
Okay. Here, that node is autonomous. What you do is you take the node and you say what the edges are, and you manipulate those edges and the nodes. Right? Anyway, you have some sort of manipulation mechanism.
Correct. Okay.
Here, it doesn't do that. Here, each node is autonomous. So you can imagine these edges disappearing, edges connecting. Imagine Neo4j, but the edges can connect and edges can disconnect. Edges can go through another channel and then connect, so it will lose its shape.
So, okay. Yeah. So if I rephrase it, this is just for my understanding.
Yeah.
A K-graph in Neo4j is just a representation of data.
Correct.
But in your case, you're evolving it to the next stage where each node isn't just a data, it also has an intelligence to take decisions on that.
Yes, exactly. And intelligence to connect the neighbor.
Got
Move out.
Okay.
Right.
Just curious, you using Neo4j itself for your actual data persistence or some other?
No, MySQL.
Oh, okay.
So all this magic happens in MySQL.
Okay.
Okay.
Interesting.
So,
got it. I get what you're doing.
So that is the whole point. Yeah, I think you got the right. I should use that, with the technology people. If you know Neo4j, that will be the nice analogy. Good point.
Antony, just a follow-up question on what has been asked. When we have been storing the data into the new Forger, so to show this kind of the intelligence, have you developed your own model? How this intelligence is coming?
The intelligence is ultimately I can go into theory. It's okay? Okay.
Yeah,
okay. So basically, if you look at, I'll go to a bit theory here. Okay. So if you look at functions, okay, I'll go mathematics. Is that okay? Or okay. So basically,
if you can go as technical as you want. That's the whole purpose of the session.
Okay. So if you look at any function, if you take, a standard algorithm, standard processor, it is basically an algebra, right? Main is actually an algebra. You give it an input and it produces an output. And it's a function, it's a good old function decomposition. One function leads to another function leads to and then there is a function reduction that comes up with the answer. I'm talking of in terms, converting a program to a good high school algebra. Correct? A program
Anthony, you can go. I mean, technical mathematical as well. I'm the maths honors graduate.
Okay. So that's what it is, right? So now here, what we do is we say, okay, instead of thinking of it as a function, you take the function into two pieces. Function has an input and function has an output. Correct? So, what does a function do? It produces an output, and then it's something else binds to it. So we take the function out, and function is divided into two pieces. And function has become a communication mechanism. So you don't look at function as a mathematical entity, but as a communication entity. So when you have a communication entity, it means it has to have two ends. It has to have a sender and a receiver, one to send the input and one. So that is what we do. So we have taken the function and made it into an interaction.
And Antony, maybe as you're telling this, right, I'm trying to rephrase it. I don't, maybe it might make sense to Saurabh. If I'm right. If I'm wrong, you tell me. So what we are looking at fundamentally, this is a deterministic rule-based model. The rules are built on it. It is not a probabilistic model.
No, it is actually
much more sense actually. Yeah. So it's basically you have defined a certain kind of the rule, and based on that, this kind of the intelligence you are driving.
No. Rule, not rule-based, communication-based. So rule means there is a series of functions that you have to run. This function deals with another function. What we are saying is the function itself, function. Okay, so I think I have to do the, let me use the whiteboard.
Do you want to use the whiteboard? Yeah, I thought that's better. Yeah. Are you able to see it there?
Yeah, so okay, so we will take a simple text. Okay, so y is equal to f of x, right? Okay, that's how we do it now. That is what a processor does. what we are saying is we divide this into two pieces. It's actually a process. There are two processes. The function sends the output and another function receives the input. And they're running in parallel. And so like chemistry, they bind when they come together. Right? This one is an input, this is an output. So you can imagine this is like chemistry. You have negative and positive, and they bind and they come together and then they form a molecule. So it is not a function, but it achieves the same thing, but concurrently.
So isn't this a semantic rule that you build like in the Sparkle language?
No. So if you what we base this on something called a pi calculus. Okay. If you look at programming, they are based completely on lambda calculus.
Okay.
So what it does is it's a symbol manipulation. You take a symbol, it does something, it produces another symbol. Then you apply, do application, and so it becomes another symbol, and it goes on and on and on and on. That's what a computer does, right? It basically symbol manipulates. What we are saying is we are modeling a process. A process consists of 2-3 agents that are running in parallel, and they communicate with each other. Okay, so let's say this is an agent. Okay. Similarly, there's another agent. How do you copy this?
You can just draw another one, no? Right next to it. Yeah, that's faster now. Yeah.
Okay.
Yeah.
Right. So you have this. Okay. So now this is a P1, and this is P2. Two processes, and they interact with you on some channel. This is what we are making. So there's a channel, and there is another channel here. So this is an agent, and this is an output. So how do you put an arrow here? I don't know. So
yeah.
I don't know. So this is let's make it I can use a pen, right? So this is output. Whoa. This sends the output, and
you could do it like this. You could just do it like this. I'm doing it now for you.
Yeah.
Yeah, this is what you mean.
Produces. Yeah. So that gives the input. And all what we are saying is these lines are actually the semantics. So all those things you saw, interactions, they are all these lines.
So when does like P1 at some point under some event has to decide to send the data to P2, right?
Correct.
Where is that happening? When does it need to take an action?
So what if P1 is spawning P2, then it will send a channel to P2.
Yeah, but how do you say when it has to do it? When does it have to do that? That's given somewhere in the language, right? In the XML file that you showed.
Correct. So I can you show that, Jagdish?
You will have to stop sharing this, I think.
Oh, okay.
Jagdish can share, yeah.
Yeah, he can show the code.
And that's what, you have been referring as communication, right?
Correct. So for example, here, we'll just tell is basically an outbound signal. Ask is an inbound signal. Okay. Now, basically, this interaction happens either from outside through the screen or from a machine from outside. Somehow, some interaction happens. Then it moves to the next step.
Isn't all these nodes state machines with events driving each other?
No. These are individual agents.
Yeah, but isn't that what state machines do? They have certain states. They move from one state to another based
Correct.
on event. They communicate their state to another
Correct.
object which is in a different state.
Correct. But what it doesn't do is, so state, yes, but this one also has a communication element to it.
Okay.
I know my neighbor also, so I can talk to my neighbor. I know the channel in which I have to talk to. So it is both the state and the connection.
Understood. Okay, got it. I think makes sense now.
Yeah. So and these are configuration operators. Choice means, okay, when this interaction happens, these are fired. Compose means all these interactions happen at the same time. Sequence means interaction happens one after the other.
So, Anthony, just extend the question which Anandan has also asked, and we have been specifying this kind of the communication or the rules, right?
Correct.
Is there any intelligence that's when the one has to connect to the another, like say over a period of time, does it learn by itself that's there is a point to connect or there is no point to connect at all?
Yes. So the intelligence is what you can give that intelligence. What should be spawned, what should not be spawned.
So basically you say like, and where exactly will define in this XML file itself, is it?
Yeah. So can you show where you could, it spawns a node, Jagdish?
I assume that there will be a condition specified there. Under this condition, spawn it, connect it. If not,
so for example, remember we have that 2-3 nodes together. So what it is it is basically one node. It spawns, then that node spawns another node, but it shares the channel.
No, actually, this part is clear to me. Why I'm saying is like when we have been talking about like, these are kind of the communication medium we have specified.
Correct.
And, every time it will go through in a specified sequence itself. Like, when this has happened, then, this is going to happen. When this happened, then this is kind of the event driven. But if you see the repeatedly, if something is happening, say for example, if the one node is spawning the another node and which is not giving any kind of the predictive response or any kind of the benefit, so is there any intelligence is involved, which can say there is no point rather than that means basically is the machine is learning by itself or not, or it is based on to the everything what I have defined it in these rules?
Machine, that is left to you. You can spawn the machine to control what you want it to learn. We are leaving it to you.
Okay, I see.
So you can machine doesn't, because you can actually build an agent, a node, which can get all the inputs and spawn a node and form a network. That also can be done.
Okay.
So the control is given to you. That is the whole idea. The machine by itself doesn't know, is a clean slate.
I see. Okay, that makes sense. So basically, like, there's no machine learning is involved where the machine keep on learning
machine
for
learning.
its body.
Machine learning is what you. Machine learning is you get the data and you tweak the weights. Here, what we are saying is you build those causation directly because you know what the input outputs are. You can build the causation directly.
Okay, makes sense.
Right. So, but there is no machine learning in terms of correlation That one is not there yet. That is what you're asking, I think, no?
Yeah. So because I've been looking for more from artificial intelligence per se, where the machine started learning anything by itself.
I think the intelligence that this application can be made as intelligent as much as the configurator wants it. It is determined by how much they want.
How much you want. How much learning do you want? What are the nodes you want to spawn? How do you want to connect the nodes? Do you want the flexibility to alter the neighbors? Do you want to build a self-organization? Do you want to build healing, self-healing? All that you can do here.
Got it. Yeah.
Because those are the needs in a supply chain, where suppose a port goes down, you basically have to work around. So you basically shut everything off, like how a human body heals itself. Cells, some other cells tell these cells to die, and they die, and then some other cells take over, and then the neighbors form. That can be done here, that intelligence. But there is no LLM based or neural network based. That is not here.
Okay. Yeah, now it makes much more sense. I'm sorry,
correct.
With the series of the question I was shooting at, but
no, because ultimately it is leading to a path that is more important. End result is more important.
Yeah, thank you so much.
So now, is it possible that interaction lead to a wrong result? Is that interactions can lead to a wrong result?
Yeah, you're reading from the questions.
Correct.
Yeah. So one of the participants asking, the learning is basis the interactions. How much time would it take for the system to mature? That is his first question. Then he has asked, is it possible that the interactions lead to wrong results? You may want to respond.
Correct. So let's take the first one. If the learning is the basis of interaction, how much time would it take the system to mature? System maturity is left to the guy who is conceiving the system. So if you are interacting with the environment and you have taken care of all the conditions of all what you see, then you would have had the responses appropriately. Now, if you see interaction that you have not tuned for, you have not seen, then obviously you're not ready for it. So that will be an area where you will not be able to respond. So somebody else will have to come and give that intelligence to you and say, okay, when this responds, you change the agent and say, if you see this in the network, you just respond like this.
So in this case, for example, let's say there is Mahindra comes up with a electric truck. That means somebody has to go and make changes for that. Electric truck has to do this, do that. It will interact like this. It will communicate like this. They have to go and add it.
Correct. So for example, we have done the bill of material. I think you're talking of a bill of material.
No. I'm talking about simple things like it's a new vehicle that has come. It has price. It has quantity. That's all.
So you created a new category, is what you're saying, as per this.
Yeah, correct.
So you're asking, like what we showed, how do you go and add a category and do that?
That has to be done explicitly.
Correct. Or you put the environment, you can put connect this to some sort of internet, and then look for some sort of new things it finds, and those keywords it can do, and it can add those keywords, and but it has to build the connections either manually or through some agent, which has to be.
Okay.
Is that what you're asking, or I hope I got the...
Yeah. No, you're correct. It has to be added. Manually, or somebody has to write some script to add it?
Somehow, yeah, it has to make sense. It will not automatically go and read and figure that out. No. That intelligence, it has to be told.
Basically, it has something has to modify that XML file to add these nodes.
Not the XML file, but the interaction. Like XML file is only the seed.
The interactions are also in an XML file only, right?
No. If you agent is just like a seed. Okay. Now you can create more and more. So for example, each of those circles, can we show the network graph? Each of these circles have agent. You don't have to go and change the network, the XML file. What you're saying is this blue node, what does it respond to? And when it responds, what does it have to do?
Okay.
So that algorithm, that response and sensing and responding is what you're writing.
Okay.
Then the system will do by itself. So your system has to listen to the environment, however, either manually through a human being or through some sort of environment, and make sense of it. So we have to have some sort of sensory mechanism.
Okay.
So that is, but once that is done, then all you will do is add a node, add a category, and it will add a new category. And it will go through all the interactions that a category has. How will it fit in the environment? You want to show that, or why don't we show one add category?
Yes. Quick check on time, Antony. We are almost up on time, but if the participants want to
it's
probably
left to the
extend by
participant.
another 5-6 minutes, we can do that. 5 to 10 minutes.
I think let him just finish this point.
Yeah.
So there is some question. The real life example. Yeah, it could be email, it could be chat, it could be SAP. It could be just agents that are outside this network, which listening outside, and then. So for example, when you create a node, like here, it creates XYZ, new node, let's call it. Jagdish, are you there? X, yeah. So what this does is it creates an agent. So now if you go to the graph, now this agent is able to interact. It can do all the interactions that a blue node does.
Understood. Okay, got it. Okay.
Okay, yeah. So that is what you're specifying in the language. What are the interactions? How will this interact with the surrounding nodes, other agents? So now here XYZ, you can go and you can connect it to another node, say Maruti Suzuki, probably. Can we connect to Maruti Suzuki? XYZ. Yeah, so you can go link with Maruti Suzuki, I guess. Then the network will change its shape.
Got it. Okay.
Then it becomes a different.
Understood. Okay, got it.
Okay. Yeah. So that is the difference between Node4j. I mean, this now you will know, the difference, right? Edges and the nodes. Yes. All right.
Yeah. Thanks, Antony.
Thank you, Anand. Thank you, Kumaran. Thanks, Saurabh. Thanks, Rizwana.
Yeah, I think this has been a very intense technical session, which is what the purpose of ShoAIcase was. And I think probably this is one session which is real. I only wish we had more people joining in to ask you more questions, but it would have definitely gone for beyond our. But this will be on YouTube. People can watch. So thanks.
And people, they can reach out to me. I'm willing to, let's talk if you want to know more. So.
Sure, we'll do that. Okay. Thank you all so much for joining.
Okay. Thank you, everybody.
Yeah.
Thanks.